All right. Up next, we have Ashton Wiersdorf. Is that pronounced correctly? Okay. Ashton Wiersdorf, who's going to tell us a bit about event-based choreographic programming.
Okay, I did push the button and.
Just don't push the button and put it back.
Maybe that's what I did. Okay. We doing good? Okay. All right. Yay. Thank you, AV people. Yay. All right. Okay. Well, very happy to be here. I am going to talk to you today a little bit about my library, Chorex. I wanted to add the THX like sound for that, but didn't figure out how to do that. Also, by way of names, so this is a library for the Elixir programming language. Hence the EX. A lot of Elixir libraries have EX. I just love all the puns we have in choreographic programming. I thought unicorn was just peak. So, here in choreographic programming, we have this beautiful model of going from a this high-level overview and splitting it out into pieces. And my library brings choreographic programming to the very pragmatic world of Elixir and production concurrent functional programming environments. To start off, it is truth universally acknowledged that a computer scientist in possession of a good theory must be in want of an implementation. I think Jane Austen said that, something like that. Chorex is a very, I don't know if very is the right word, but it's much more of a pragmatic focused system. And I've already made a version of Chorex. I'm going to talk to you a little bit more about new directions I'm taking Chorex. To do this, I went around and looked at a bunch of different distributed systems. So Elixir libraries mostly, but a few other systems as well. And what I really wanted to do was to see what can't I do in Chorex or some other choreographic programming language. I found a few compelling applications, and so then I thought, how would I want to program these systems? And what would I need in a choreography to do that? So I wrote some fantasy programs and eventually found some core building blocks that would help me express all the patterns that I wanted to. So in quick order, the building blocks were I wanted event handlers. If something happens unexpected in the system, I want some other part of the system to be able to respond to that. Another one was some way to control who's participating in a system. Systems create and destroy processes all the time. And finally, to make these two things happen, I realized I would need first-class process references. I'll get more into what that looks like. Now, to set expectations, I've kind of got this path up to event-driven choreographies. I'm not quite there yet, but hiding in the bushes, we found this lovely thing called first-class process references. So that's what, so we've got first-class process references working in a lot of ways. It's awesome, and I'm still working on implementing the rest of it, but I'm optimistic. So without further ado, let's talk about one of the most compelling use cases I found for something that I'd like to write with a choreography. So I'm going to build a web server. This design is borrowed from a web server library for Elixir called Thousand Island. The way Thousand Island works is like this. You have your server, and you have a listener process that's listening on the operating system port. When somebody comes in and tries to make a connection, that process goes, oh, got a new connection, and it grabs a process from this pool of acceptor processes. These are all just waiting. And that acceptor then does the TCP handshake. So now you on your server, you've got a socket, which is great. And then you take that socket and you wrap it in a process to manage its lifetime. So now we have, that's why it changed from dotted to a full thing. Now you have a process managing the life cycle of this socket. You can send this process a message, and it will forward it back over the TCP connection, whatever. So now you've got a process client, and then the acceptor spawns another process meant to manage the life cycle of the web application itself. And these talk back and forth to each other with request, response, request, response. And ideally, we'd like to kind of partition this off into its own little choreography. Once this is done, the acceptor moves back into the pool and is ready to keep working. This is nice, both because it can accept requests very, very quickly, but also if something, say, happens to the client, like the client shuts down unexpectedly and crashes, then the app worker can cleanly clean up whatever resources are left over. And vice versa. If the app crashes, then the client could notice that, send a nice 500 error message back to the client, and then shut itself down gracefully. So there are a few aspects of this that are tricky. First, you need to be able to spawn new processes. You need to involve new processes in choreographies, and you need to be able to respond to events. So here's the choreography I wrote. Now this is aspirational. That said, I said this slide is taken almost verbatim from my dissertation proposal. I say almost because I've updated this choreography, and it's a lot closer to what we're actually able to implement. So I'm pretty optimistic that most, if not all of this, will make it into the final version. So choreographies and stuff are kind of grow up a little bit. I don't know. You start off with these role definitions that talk about the kind of actors in your system, and they each you might need some of these actors to know about other actors. For example, the client should know about its app worker, and the worker should know about its corresponding client. This becomes important when we get to events. Here's the choreography for the main listen loop. You've got the listener process. L is the listener process. It's got the OS socket that listens to. It grabs an acceptor process off of its pool, round robin style, and holds on to that until somebody comes knocking on the door. It's the LCON. And then it starts up a little sub-choreography. So there's actually sub-choreography right here where it says, hey, acceptor, take the connection, go. And then it goes just back, recurses back, and keeps listening for new connections to come in. This is where the acceptor creates a client and worker. I've deleted the bit where it does the TCP handshake, but the idea is it does a TCP handshake, hands that off to the client worker, and then the app can start running. And so then the app is pretty basic. Oh, this is the setup application. In this place, the client monitors the worker. So if the app shuts down, then the client process can send a 500 back to the web browser or whatever waiting on the other end. And then here's the application loop. It's pretty simple, even though it's a little bit longer, but this model is like a stateful application. And then finally, here are the events. This top one models if the client gets a message that its app worker has gone down, then it can send a 500 error back. And then the client, if the client shuts down suddenly, then it can clean up. This is probably the part that needs to change the most. So if anybody has any inspiration on what should go here, I would love to talk to you after. So to recap, some of the new things in this are, first you have first-class actor references. I've got some expression in the choreography language that next acceptor references another actor. I also make new processes in addition to pulling them off of lists and whatnot. And then we've got these event handlers. So those are the new things in Chorex v2. I'd like to talk to you a little bit about how we actually do macro expansion. Projection. We use macro expansion to do projection. And that, so Elixir's got a fabulous macro system. It's AST based. Its macros are hygienic, and they're procedural based macros. And what this gives us is a lovely language integrated choreographic programming system. So it kind of sits at this little, this funny in-between space. It is a library. You install it like a library. All the syntax highlighting works like it's embedded DSL. You get all of the IDE features and whatnot. But in addition, the macro expansion phase acts as like a compiler step. And so we can do analysis on it. So you get wonderful error messages in the terms of the language that the IDE can understand, even though it's your embedded domain-specific language. So it's pretty neat. Now, onto Elixir's process model. So Elixir is based off of it runs on the Erlang virtual machine. And so it has really lightweight processes. Each process has a mailbox, and processes can also monitor each other. So if one process goes down, then another message can be notified of that. This is fabulous. Now there's a special flavor of process called a gen server. And a gen server is just a library to realize a common pattern with processes. It's basically a process that can have some state and take action in response to messages that come in. And this turns out to be a great model for actors. Here's an example of how a gen server might look. You describe a module. So here's a module to like make a counter where you can say like, hey, increment, increment, increment. Okay, give me the count and reset yourself back to 0. So yeah, you say use gen server. Says I'd like to make a gen server, please. They all have some initialization steps. So this is just setting up like the start count. And then there are different ways that you can send messages to the gen server. This one would be like, if I get a message that is the Atom Inker, then I add 1 to my state. And it does a functional update, so like there's no mutation under the hood. But nice and clean. It gives you a nice stateful process. And here's another one where if you, this is when you get the message get and reset, send back your state, your counter back to whoever called you, and then your new state should be 0. So that's all with that. There's a tricky bit here, and that is with gen servers, you don't want to stick an explicit receive inside of a handler, because that might break things with how the gen server would work. So we had to find a way, and this is using Chorex v1 notation here. We had to find a way to make these receives work. So anytime you do a receive in Chorex, it actually has to get split across 2 message handlers. So for example, here's the first half of the choreography where Bob says something and sends it to Alice. But then, and that's the top function there. But as soon as Bob wants to receive the price from Alice, he has to have a separate handler for that. And these two get kind of tied together with just some kind of UUID, some identifier to tie them together. And all this gets bundled up in the gen server state, and there's a little bit of a runtime that manages this. Please see our first paper for more details on this. Anyway, but the point is this is really complicated, and it makes projection really tricky. So why would you want to bother with gen servers at all? Well, for starters, gen servers are very easy to monitor. And the second thing is that they can do out of order message handling. The gen server runtime handle will, when it gets a message from another actor, it puts it inside of its own mailbox so that if the messages arrive out of order, it can reorder them or handle them in the order that it's expecting to. We use sieves, kind of like Ozone, to make sure that messages come as expected. And finally, these gen servers can actually participate in multiple sessions at the same time. The way the gen server state works is that they have a network, which is just like what other processes they know about. They have this inbox, again, that you can reorder. They keep track of what module is implementing all of the local code of the actor. And then they also keep track of all the sessions that they know about. So this is just a map of a bunch of sessions, and each session holds the local variables at that point, as well as a separate stack. And so this is kind of like it's like a gen server, but it's got multiple versions of itself that it can teleport between. And each of these are keyed with something called an sRAID. Yeah, they're all keyed with that. The sRAID stands for session ID, role ID, and actor ID. So the session ID is generated when you instantiate a new choreography. That's the session. The role ID is like, am I a worker? Am I a client? Am I a database handler? Am I a bookseller? Whatever. And the actor ID is a unique token for the choreography. I'll get into that in just a minute, what that is, after I talk to you about some new problems that I found. Because I was like, I would love to write this choreography, and then all these new problems started snowballing. The first one is we need something like a role checker, not like a type checker, but it's a role checker, because the role Alice is up here, but down here in the choreography where I'm trying to talk about a process that implements Alice, there's no Alice right there. The actor names aren't where we need them anymore to do projection, so we use this signature right here and perform something kind of like a type check to propagate that A refers to a process named Alice. Now, I would have said that Elixir does not have types, and so like we don't get this for free. Elixir 1.20 dropped last week, I think, and so now we have types in Elixir. So, but still doing something like this is a little bit like there's still no user annotations, so there's still a ways to go with that. But I am curious to see like what I can do with Elixir's new type checker. But anyway, there's also some more stuff here that I'll get to in like 3 slides. Anyway, so we have a custom role checker. We also sometimes need explicit role casts. So like here, this could be synthesizing a new process identifier. And there shouldn't be anything wrong with that, but the problem is the role checker doesn't know what role we're talking about now. So if you do need to know what it is, you can annotate it like that. And the double colon is an infix operator in Elixir, so the Mackers are happy. So role checker. The second challenging issue was what if a role shows up more than once in a choreography, like this? Imagine you've got 2 worker processes, and they need to switch the jobs that they're working on for whatever reason. So you've got worker 1, it's here, and then you've got worker 2, and that's where it's at. They're both called worker. Remember how I talked about the S-RAID, and it was session ID, role ID, and actor ID. So these get unique actor numbers, and so when it projects, the projections have, there's some more of the rest of the S-RAID is right here, but then there are 2 copies of this function inside of the projected module. And so this one will handle the actor ID 1, and this one will handle when it's the actor ID 2. And so it will dispatch between them. And the neat thing is this works even in like really turgid situations where here we've got 3 workers, worker 1, 2, 3. Worker 1 sends 2 to worker 2. Worker 1 sends 3 to worker 3. Workers 2 and 3 both send messages back to worker 1, and then worker 1 combines them. So we should expect 2, 3 at the end. Fun thing is, I have gotten this working whether or not you instantiate it with 3 separate processes or 1 process in each of the 3 roles. It keeps the variables and stacks separate. So, yeah, path torture, yes. I don't think I propagated that up here, but yes, path torture. So that was a fun headache to resolve. And then one tricky issue, and there's some relation to knowledge of choice with this. If I create a new process up here at the top and then call run job on it, how does that process know where to find the other processes? I'm calling it right here. How does it know to find the other processes? How does it know that's even involved in a choreography? It's just floating in the void until somebody talks to it. The answer I came up with is when you do a function call, that's when you can wake up a referenced process. This is very important in the example that we showed earlier where we have a client and a worker that just get like produced out of the void, ex nihilo, and now you're like, okay, now go and start off this choreography. But now there's a question of who notifies the actors. Now we could have like some central process to to do this notification and help introduce all the processes to each other. There's some prior art that does something like this with durable processes. But I want to try to avoid that. So the limitation I came up with was all processes going into a function have to be either all top level or there has to be one hub. All top level means that you're working with variables that are just like variables by themselves, and presumably they should already know about each other. When you kick off a choreography, there's one process that's going to do that, and so it's going to introduce everybody. So if you're just working with a subset of those processes, they should already know how to find each other. No issues there, at least so far. The one hub is here. I'm trying to call a function with A. B is not involved here. Oh, I forgot to mention this. This first argument to the choreography is the set of process identifiers that you want to instantiate the choreography with. Sorry, I meant to put that earlier in the talk. But so A is a process. X and Y are also processes, but B knows their process identifiers. A does not. So that means B is the hub in the situation, and so the projection for B will contain all the code to introduce and wake up X and Y and let A know what their PIDs are. So that should work. Here's where we run into trouble, where we have processes that don't have a common hub. I thought that we might do something automatic with this, but it turns out it'll just be easier to, and it's better to give the programmer control of who is the hub, how do the process identifiers get there, etc. So those are the three headaches that I've kind of overcome. And more challenges remain. For example, what is the right model for events? Should we just allow arbitrary interrupts? I'm still not sure about that. Can we find other ways to wake up actors? And maybe you guys have seen something that I have missed that will come and bite me. But anyway, so happy to talk about these. Thank you very much.
We have a few minutes for questions.
One basic question to start. Why would you want to have three? Why do they all have the same name in that picture? Why don't you call them worker 1, worker 2, worker 3?
That would then be 3 different roles.
Why do you want them to? Why do you want them to share the role, same role?
So we've got a bunch of in this instance we have a bunch of processes that have this that we want to be interchangeable with each other. Right.
So they all function as the acceptor.
They all function as the acceptor, right? Maybe you have a pool of workers, and you want them to have like a uniform interface, but then maybe one of them decides like, hey, you know, I don't have a GPU, but that worker, I know that worker's got a GPU. Let's switch roles, but they've got the same API to the system, and so I don't know.
I guess my
Also, why not?
It's like a sub-role sort of thing. Like we're all workers, but in the context of run, this is worker 1, this is worker 2.
Yeah. That is kind of implicit, though, with the actor IDs, as these get under the hood a 1, 2, 3. So, yeah. Is there like a sub-role? That's an interesting idea, though, having like subtyping for actors. Okay.
All right. Maybe one last question while the next speaker gets set up? Or you have a question and or the next speaker?
So can you elaborate on why you need the no common hub rule? Because A, B, and C are all present and know that we're going to go into the choreography compute. So why can't they all just wake up their children?
They might have more than just those children. They could, but how are they going to communicate? They can wake up their children. That's not an issue. But then, how are their children going to be introduced? Whose house is going to host the play date? Good question.
Right.
Right.
Let's thank Ashton again.
Thank you.